Hello friends, dear learners and my dear student. First of all, I take an opportunity to welcome you on the lecture Ultraviolet Visible Spectrophotometry. I am Dr. S.R. Labhade, working as Associate Professor in the Department of Chemistry. Student, in previous lecture we discussed the applications of spectrophotometry in titrimetric analysis. That is a photometric titration. We already discussed types of photometric titration and their applications in. Student, in today's lecture we discuss another applications of spectrophotometry. We know that spectrophotometry is a important tool of qualitative and quantitative analysis. Therefore, both qualitative as well as quantitative analysis is done in a spectroscopy or spectrophotometry. Sample is irradiated with electromagnetic radiation. At specific wavelength, sample shows absorbance. The wavelength at which sample shows absorbance is its identity, and amount of radiant power absorbed at that wavelength is related with the amount of material present in the sample. In spectrophotometry, qualitative analysis is carried out, that is, identification of sample is carried out on the basis of wavelength of absorption. Therefore, in spectrophotometry, the wavelength of absorption is identified by using a absorption spectrum. Absorption spectrum is a graph of, our absorption spectrum is a graph of absorbance of a sample, as a function of wavelength of analysis. This graph is called as spectrum, and here the technique is called as spectroscopy. Therefore, absorption spectrum is a fingerprint of the sample, and we can utilize it for the identification. That is a peaks which are obtained on an absorption spectrum that signals the wavelength of analysis. Therefore, we can identify the material on the basis of absorption peak obtained in the absorption spectrum. So, the qualitative analysis in absorption spectroscopy is done on the basis of the absorption peaks obtained at a specific wavelength. Student, in previous lecture we discussed the properties of electromagnetic radiation. Electromagnetic radiation, that is a one form of energy, and this electromagnetic radiation have a corpuscular nature, that is a particle, as well as wave nature. Therefore, here the particles which are present in electromagnetic radiation are called as photons, and sometimes those are also called as quanta. When electromagnetic radiation interacts with sample, electromagnetic radiation absorbs these photons. Therefore, when electromagnetic radiation are absorbed by the sample the photons are absorbed by the sample. The absorbed photon is destroyed and that energy is utilized by the sample. Therefore, the absorbed photons are destroyed and energy is taken by molecule for either rotational or vibrational or electronic transition. Therefore, here this energy is utilized by the sample either for its rotation transition, vibrational transition or electronic transition. Therefore, those energy is utilized for electronic excitation from lower level rotational level to higher level rotational level, lower level vibration level to higher level vibration level, or lower level electronic level or ground state electronic level to excited state electronic level. Therefore, this energy is utilized by the sample for any one of this transition, and therefore here this absorption spectrum is obtained. Spectrum is obtained. That means here this spectrum is a graph like this. Here this is absorbance as a function of wavelength. Here we have different peaks from IR to visible or to the ultraviolet like this. Therefore, here molecule undergo different types of transition at a different wavelength because each transition requires different energy. Therefore, here different transitions are occur and therefore different absorption peaks are occur on the spectrum, and that is the identity of the material. Student, now we discuss how electromagnetic radiations are absorbed by the sample and how those are utilized for the electronic excitation in the molecular species on the basis of molecular orbital theory. We know that here when any molecule is formed, that will be formed by the combination of two or more electrons. That will be formed by the combination of two or more atoms. Therefore, here, suppose for example, we have here a formation of a particular molecule using these atomic orbitals. This is atom first, atom 1, and this is also a atom 2, or this is atom 1, this is atom 2. Here atom 2 have one extra orbital. Then when these two atoms combines together, there is formation of bonding molecular orbital. That is this is 2s, 2p, z, 2py, 2px. Similarly, this is 2s, 2px, 2py, 2pz, and this is non-bonding molecular orbital. Therefore, here this is non-bonding atomic orbital. In this case, when 2s orbital of one atom combines with 2s orbital of another atom, it gives sigma 2s bonding molecular orbital and sigma star 2s anti-bonding molecular orbital. Similarly, here 2px gives sigma 2px, that is bonding molecular orbital, and similarly sigma star 2px anti-bonding molecular orbital. Similarly here pi gives pi 2py and pi, here this is pi 2py, pi 2pz. Similarly here this is pi 2py and pi 2pz, and this orbital will be present as a non-bonding molecular orbital. Therefore here, according to molecular orbital theory (MOT), when two atoms combines together, there is two or more atoms combines together, there is formation of a molecule. When two or more atoms combines with each other or involves in bond formation, atomic orbital of one atom and atomic orbital of second atom undergo overlapping. Number of atomic orbital involved in overlapping, same number of molecular orbitals are formed. Therefore, this is a energy level diagram which represents the formation of a particular molecule on the basis of molecular orbital theory. Then according to Hund's rule and above principle, electrons are distributed in this orbital with increasing energy. Therefore, first of all, a ground state electronic energy levels are filled or molecular orbitals are filled. Then, if electrons are remaining, then some electrons are filled into anti-bonding molecular orbital. Therefore, more electron in bonding molecular orbital, that gives the stability to the molecule, while more electron in anti-bonding molecular orbital, that gives the instability of the molecule. Therefore, here, according to Hund's rule and above principle, electrons are successively added into the molecular orbital with increasing energy. Sometimes here, molecular orbitals are completely filled and anti-bonding molecular orbital may be empty. Sometimes, some molecular orbitals as well as some anti-bonding molecular orbitals are filled. But when there is free or vacant molecule, anti-bonding molecular orbital, then when radiant power falling on such a molecule, these electrons get promoted from bonding molecular orbital to anti-bonding molecular orbital. And for this purpose, energy is required, that is absorbed from the electromagnetic radiation. In this case, when a particular molecule is irradiated with electromagnetic radiation, that will absorb only those energy which is required for electronic excitation from this level to this level, or from this level to this level, from this level to this level, or this level to this level. Therefore, energy that is absorbed from the electromagnetic radiation, that is totally depends upon the energy gap between the bonding and anti-bonding molecular orbital. On the basis of this, here for electronic transition sigma to sigma star or this sigma to sigma star requires highest energy. Then this sigma to here, this is pi star. Sigma to pi star require little bit lower energy. Then pi to pi star require less energy, and non-bonding to pi star require minimum energy. All these different forms of energy are absorbed from the electromagnetic radiation. That means those electromagnetic radiations are absorbed by the sample, which provides a photons whose energy is equal to the energy gap between these levels, which is required for the electronic transition. Only those radiations are absorbed by the sample. According to molecular orbital theory, when any molecule is formed, that is formed by the combination of two or more atoms. We know that according to atomic number, each atom have a different electrons. Therefore, when combining atoms are different, their electron number is different, and therefore when these orbitals are formed by those atoms, the distribution of electron is governed by the number of electrons present in that atom. And therefore here this molecular orbital theory tells us that the energy gap between these bonding molecular orbital and anti-bonding molecular orbital is totally governed by the combining atoms, or it is totally governed by the type of molecule thus formed. Therefore, every molecule have a molecular orbital, but that molecular orbital are not exactly same energy difference. Energy difference between these bonding molecular orbital and anti-bonding molecular orbital for molecule to molecule, this is different. Therefore, each molecule will absorb at a different energy or at a different level, and which is the identity of that substance. Student, this is the molecular orbital energy level diagram of a particular molecule that consisting of anti-bonding and bonding molecular orbital, and when substance absorbs energy, electrons are promoted from bonding molecular orbital to anti-bonding molecular orbital. From this figure it is observed that here for sigma to sigma star transition, that is 2px to 2px star or 2s sigma 2s to sigma star 2s, that require highest energy. That means sigma to sigma star, this electronic transition require highest energy, and this will be taking place below 150 nanometer, that is in vacuum UV, that is below 150 nanometer. This type of transitions are takes place, and those are shown by only single bonded compound. Single bonded compound shows this type of transition, such as carbon hydrogen or carbon carbon bond. Such a type of bond shows this absorption that would be taking place below 150 nanometer, that is in vacuum ultraviolet. Second thing is that here second type of transition is here sigma to pi star. Therefore sigma to pi star, this type of transition requires less energy, that is less than this, and it will be takes place in between 150 to 250 nanometer. Here 150 to 250 nanometer, that means here it is also taking place in ultraviolet region, and therefore here the nitrogen, sulfur, oxygen, chlorine, bromine and iodine containing compound shows this type of transition. Below 150 to 250, this type of transition is shown by such compounds or compounds having these atoms. Similarly, third type of transition is pi to pi star. That is pi to pi star. This type of transition requires energy less than sigma to sigma to pi star, and this will be takes place in between 380 to 480 nanometer, and it is shown by all double bonded and triple bonded compound. Double bonded and triple bonded compound shows this type of transition because pi bond is present in double bond compound and triple bond compound. Therefore, pi to pi star transition is shown by the double bonded and triple bonded compound within this region. And fourth type of transition, that is non-bonding to pi star, require minimum energy, and this transition takes place at the end of visible region, that is takes place at 700 to above or longer than 700, and it is shown by the compounds having a non-bonding electron like this, or this type of molecule having a non-bonding electron. This type of transition is shown. If we consider the energy is increasing in this order. Therefore, according to molecular orbital theory, sigma to sigma star transition require highest energy that will be taking place in vacuum UV. That means only this radiation provides this energy for the transition. And here, all single bonded compound shows this type of transition. One of the most important advantage of this is that single bonded compound shows absorbance below 150 nanometer. Therefore, we can easily use single bonded compound as a solvent in ultraviolet and visible spectrophotometry. Because solvent absorbs below 150 nanometer, then we can easily measure the absorbance above 182 onwards. Therefore, here single bonded compound shows sigma to sigma star transition because sigma bond is present in a single bonded compound only. Similarly here, sigma to pi star, that will be taking place 150 to 250 nanometer. Nitrogen, sulfur, oxygen, chlorine, bromine and iodine containing compound shows this type of transition. Then pi to pi star transition is shown by the double bonded and triple bonded compound within the range 380 to 480 nanometer. Similarly here, non-bonding to pi star, that means this much, non-bonding to pi star require lowest energy, and this type of transition taking place at the longer wavelength, that is at the end of visible range, that is above 700 nanometer, and compound containing non-bonding atoms shows this type of transition. Therefore, here molecular orbital theory tells us the probability of electronic transition. That transition occurs at a specific wavelength. Therefore, this is the identity of the substance, and we can utilize this identity for identification of the compound. Suppose we have a single bonded compound, and here that shows absorbance below 150 nanometer. Actually, absorbance is not measured 150 nanometer, but we have a spectra of that particular compound and its absorbance is below 150 nanometer. Then we can conclude that that is a single bonded compound. Another peaks from the absorption spectrum also tells us the additional information, and that we easily extend for identification of the molecule. This is all about the absorption spectrum and molecular orbital theory for the identification of molecular species. Student, now we discuss the qualitative analysis by means of absorption spectra. Student, when electromagnetic radiations are absorbed by the sample, that is absorbed at a specific wavelength, which is the identity of the substance, because that energy is utilized by the molecule for such a type of excitation of the electron. Therefore, here we discuss actually how the qualitative analysis is done in U visible spectrophotometry. Student, according to B.S. law, absorbance is equal to epsilon into B into C. Suppose, for example, we have a solution whose concentration is fixed, whose path length is fixed, and if we measure its absorbance at a different wavelength, then we have a different value of absorbance. One value of absorbance is different at a different wavelength. That means here the epsilon, which is called as molar absorptivity, that will be different at different wavelength. Therefore, value of molar absorptivity determines the value of absorbance. Therefore, when solution have fixed concentration and fixed path length, when we measure its absorbance at different wavelength, then we have a different molar absorptivity, and therefore the value of absorbance is different. Therefore, molar absorptivity, that is a factor governed by the wavelength of analysis. And here the absorbance is maximum. Absorbance is maximum at the wavelength of lambda max. That is a wavelength where that particular species shows maximum absorbance. Therefore, absorbance maxima that will be occurs at the lambda max. Therefore, here the molar absorptivity will be called as epsilon max at lambda max. Therefore, here epsilon, that is a molar absorptivity, which is a maximum at a lambda max. And therefore, here molar absorptivity, that is the identity of the material, because it is determined by the wavelength of analysis. It is said that some compound is transparent to that wavelength, or that means it does not absorb at that wavelength. At that time, we are saying that the molar absorptivity of that compound at this wavelength is 0. That means if this value is 0, absorbance is 0. Therefore, if substance does not absorb at that wavelength, then we can say that molar absorptivity of this compound at this wavelength is 0. Therefore, value of molar absorptivity directly determines the absorbance. And this absorbance or this molar absorptivity, that is maximum at the wavelength of lambda max, where that substance shows the maximum absorbance, means that energy is utilized by that particular molecule for electronic excitation. Here this absorbance maxima, that will be affected by different factors, and we discuss what are those factors that affect the value of absorbance maxima. The position and intensity of the absorption maxima, that will be governed by different factors, and that will be shown by the chromophore present in the compound. Now we discuss what is chromophore. Chromophore is a group of atom in a molecule that shows the absorption of absorption of electromagnetic radiation. This group which is present in the molecule, it is called as chromophore. Therefore, chromophore, that is a atom or group of atom present in the molecule, and that actually involved in the absorption of electromagnetic radiation. And because of that, molecule undergo either here sigma to sigma star, then sigma to pi star, then pi to pi star, or here n to pi star type of transitions. Because here this particular group of atom present in the molecule, that is responsible for this type of transition, and therefore that particular group absorbs electromagnetic radiation, and that is called as chromophore. Therefore, chromophore, that is a group of atom in a molecule actually involved in absorption of electromagnetic radiation. Here, this chromophore, when it is present in contact with different types of molecules, that also affect the absorption maximum of the compound, and that compound is called as oxochrome. Therefore, oxochrome is a atom or group which does not absorb electromagnetic radiation, but present with chromophore affects the position and intensity of the absorption spectrum, absorption maxima of the compound. Therefore, here this is a the absorption maximum of chromophore may be shifted to longer wavelength, may be shifted to shorter wavelength. Sometimes the intensity of absorption is increased, sometimes intensity of absorption is decreased, and this type of effect is observed because of the oxochrome. Therefore, we discuss the effect of oxochrome on a absorption spectrum. Here oxochrome, generally these are the molecules, oxochrome, having such a type of group, hydroxyl group, then NH3 group, then here ketonic group, or NHR or NR2 type of group. Therefore, generally these are the solvent molecules having such a type of group, and that directly affect the absorption spectrum. Now here, suppose for example, we know that benzene, that is a aromatic compound that absorbs at 250 nanometer. Sorry, lambda is 255 nanometer. Benzene absorbs at this wavelength, showing epsilon value only 203 liter per mole per centimeter. But when we add here NH2 group in the benzene, then it becomes a aniline. Therefore, here this aniline that shows a epsilon value at 280 nanometer. That shows the absorption maximum at 280 nanometer with epsilon value 1430 liter per mole per centimeter. This is because of addition of NH2 group in a benzene. Initially, benzene absorbs at this wavelength, having lower value of epsilon. The absorption maximum shifted to longer wavelength, and here the molar absorptivity is also increased. That means here absorption maximum shifted to longer wavelength, as well as epsilon value is increased, means absorbance is increased because of addition of this NH2 group. Why this happens? Because here this nitrogen have a lone pair of electron, and because of the lone pair of electron, conjugation in the molecule is increases, and therefore absorption maxima will be taking place at a longer wavelength. The position and intensity of absorption maxima of a chromophore that will be changed because of the presence of oxochrome, and that gives the different effect. That we discuss here. First effect is called as bathochromic shift. Bathochromic shift it is also called as red shift. Shift in absorption spectrum. Shift in absorption spectrum towards the longer wavelength because of addition of oxochrome is called as bathochromic shift or red shift, because here absorption maxima shifted towards a longer wavelength where red color is present or red color wavelength is present. Therefore, it is called as red shift. Therefore, bathochromic shift or red shift is a shift in absorption spectrum towards, absorption, not a spectrum, shift in absorption maxima towards the longer wavelength because of the addition of oxochrome is the bathochromic shift. For example, here in this case, here this is a absorbance and this is a absorption of a particular compound at this wavelength. Then here if we have added a oxochrome in this molecule, then this absorption spectrum is get shifted towards the longer wavelength like this. Now here initially absorption maxima it has lambda 2, lambda 1, now it is at lambda 2. That means here shift in absorption spectrum towards longer wavelength, that is called as red shift or a bathochromic shift, and this particularly observed when chromophore is present a ketonic solvent or ketonic compound or carboxylic compound. When added in alcohol, this type of transition or this type of shifting takes place. That means here carboxylic group, carboxylic compound, absorption maximum of carboxylic compound shifted to longer wavelength due to the addition of alcohol, and this type of effect is observed. This is called as bathochromic shift. Second type of shift is called as hypsochromic shift. Hypsochromic shift, that is shift in absorption spectrum towards the shorter wavelength. Because of addition of oxochrome is called as a hypsochromic shift, and hypsochromic shift is also called as blue shift because ultraviolet radiation have blue color, therefore it is called as a blue shift. That means initially the compound have absorption maxima here, that gets shifted to here. That means here the addition of oxochrome shift this absorption spectrum from lambda 2 to lambda 1. Therefore this shift is called as a hypsochromic shift or a blue shift. For example, we know that aniline, that is absorbs at here 285 nanometer. When HCl is added into aniline, then it gives aniline hydrochloride, that is NH3 plus Cl minus, and here this will be absorbed at 200 nanometer. Therefore this blue shift is because of the addition of hydrochloric acid. Therefore here the conjugation which is occurring because of the presence of lone pair of electron on the nitrogen, that is get cancelled because here HCl is get added at the position or along with the NH2, and therefore here absorption spectrum shifted from 280 nanometer to 200 nanometer. This is called as blue shift or a hypsochromic shift. Now we discuss next type of effect. With the bathochromic shift and hypsochromic shift, another two effects those are observed when a oxochrome is added into the chromophoric group, and that is first effect. That is a third effect is called as a hyperchromic effect. Hyperchromic effect, that is the effect of increase in absorbance intensity because of addition of oxochrome. Here oxochrome increases the absorption intensity because it increases the conjugation in the molecule, and this will be represented like this. Here this is the absorbance taking place at a specific wavelength. Suppose this is a absorption peak for that compound, and when oxochrome is added, then this absorption maxima is increases in this way. Therefore here chromophore plus oxochrome, that increases the absorption of this chromophoric group. This is a chromophoric group. And here this type of effect is observed when this compound is called as pyridine, and here it shows lambda max, absolute value equal to 2750, but 2-methylpyridine, that is like this. This 2-methylpyridine shows a absorption maxima at 3560 per liter per mole per centimeter. Therefore, here absorption maxima is increased. Because absorbance is increased, epsilon value is increased. And therefore, here this effect is called as hyperchromic effect. That is increasing absorption intensity of the chromophore. Generally, many inorganic or organic quantitative analysis in spectrophotometry is performed by this mechanism. That means in that case, sample is reacted with the reagent and that reagent acts as an absorption. Reagent increases the absorption intensity of that particular chromophore, which does not absorb the ultraviolet radiation. Therefore, here this type of reactions are utilized for a direct measurement of the analyte in the absorption spectroscopy. Second type of effect is called as hypochromic effect. Hypochromic effect is effect of decrease in absorbance intensity because of addition of oxygen. Therefore, initially this is a chromophore whose absorbance is more. Now, when it is linked with the oxychrome, then absorbance is get decreased. This effect is called as a hypochromic effect. For example, this compound that is called as biphenyl, 2-benzene. This is biphenyl compound that have a more value of epsilon. And here this another compound is derivative, that is when methyl group is attached here, it shows the lower value of epsilon. Therefore, here chromophore, its absorption intensity is decreased because of addition of this CH3 group at the 2 position of this biphenyl compound. And therefore, here the hypochromic effect decreases the absorption intensity, and this method we can utilize in indirect spectrophotometric analysis. That means in that case we have a chromophoric system. With the addition of reagent we are decreasing the absorbance. Then a graph of absorbance as a function of addition of titrant or a photometric titration type of titration is carried out, and that is a effect of hypochromic effect. Student, with this we discuss the home assignment, and from this study you can find out the answers of following question. Number 1, how qualitative analysis is done. Qualitative analysis is done in spectroscopy or spectrophotometry. Then define chromophore and oxychrome. Then state and explain the following terms. State and explain the following terms with example. Number 1 is bathochromic shift. Number 2 is hypsochromic shift. Number 3 is hyper shift. Number 4 is hypochromic shift. Hypochromic shift. From today's lecture, you can find out the answers of this question. With this, we stop here. Thanks for joining with me. Keep learning. Happy learning.